If I set the ball right here, it will slowly gain speed. Okay. And it's going to come over here and not quite go off the edge of the ramp. It's because it's not gaining speed. It's not accelerating at a uniform rate. So my first question is going to be, how do you know it wasn't accelerating uniformly? Okay. Now, if I prop up this end with a domino, I'm going to have enough slope. Bomb will. Oh, man. You know, I've got a flaw in my design here. See if I can somehow manage. I don't know if this is going to work either. Okay, now it's too slopish. Oh man, I got to think quick. And my brain just about isn't up to it this morning. Normally I have this thing leveled, but the contraption I have to walk on isn't real cooperative with that because the rug keeps pulling the board out. So I've got to put an anchor in the wall and use a little bit of strength. And I haven't had time to put an anchor in the wall. I have the tools with me right now. Okay. Anyhow, again, let's try this again. And you notice how you got to adapt. You know, we're having lab Friday. You guys are pretty good at adapting in your first lab, so you'll have things to adapt to. Okay, you got to see stuff like this. But anyhow, and so the ball accelerates down the ramp. Now I'm going to have to run in front of it, catch it at the other end. There it is. Now, my question is, first of all, how long did it take the ball to roll? Okay, I'll let you observe it once more and just get your estimate. And you can tell me how fast it's going at the end, assuming uniform acceleration. Now, we know that the acceleration isn't completely uniform because of what we saw before, but it isn't that far off. And there's enough slope here that that little bit of non-uniformity in the acceleration isn't going to make any difference that you're likely to observe without some serious instrumentation. Okay. So I'm going to release it. As soon as I release it, I'm going to move so you'll know when I release it. Okay. Ready? Okay. So write down how long to the nearest tenth of a second you think that took. And then estimate how high this is. Okay. Now, I'll tell you, my hand stretches around 20, maybe ideally 22 and a half centimeters from my extended pinky finger to my extended thumb. So I'll call that about 20 centimeters. You can estimate this distance. Then I didn't really ask you to attend to it this time because it's going to roll at the same time. It's the same situation. Whatever time you estimated is valid. Okay. So we're going to attend it stuff. Okay. So we'll be able to do the calculations. Then I want to know how far it goes between the time the middle of the ball is at the end of the ramp and the time it hits the floor, the table. Okay. Are you ready? Okay. Make sense? Got an estimate? You're not gonna estimate 4 meters here. You're gonna estimate something, it's probably less than a handspan, okay? So in the 20-meter handspan, how far did it go between leaving the edge of the ramp and landing? So how far did it fall? How far did it go? Then you're gonna take that information, and this is your quiz. I find my chalk. You have estimates. Those estimates imply, from those estimates, you can conclude the acceleration on the ramp. So you can calculate that. Velocity when it's leaving the ramp. I think I gotta get rid of that picture in the camera. No, camera wants to go out of focus. Also, I need to bring the camera back up. Oh, come on. I think we can just about live with it there. Okay. Okay, velocity leaving ramp. This really isn't a table. We'll call this the tabletop, right? Otherwise, I'd have some other term. I don't even know what to call it. Shelf, kind of a shelf. Um, and then you can calculate the average horizontal velocity. While falling. Then we want to identify inconsistencies because it's next to impossible that your estimates will be totally consistent. That is, acceleration on the ramp should determine how far the thing went after it went off the edge of the. Okay. And how far it went off the edge of the ramp should tell you how fast it's going at the edge. Okay. And all that ought to be consistent, but it won't be based on your estimates. Okay. So see if you can answer these questions. Yes, there was a question there. Let me. Okay, so if I count it, I count 1,001. Okay, stay a little less than 2.5 seconds. We'll call it 2.5 seconds. That's 20 centimeters. That's ballpark 10 centimeters. You have a better angle on it than I do, and I'm not going to lean over and make an estimate. You can see it. Okay. And you can see it better than I can up close because you have more Yeah, the parallax isn't as much of a problem. But I think it's around 10 centimeters. Um, so okay, the 90 centimeter ramp, I gave you that, 2.5 centimeters from rest, down the ramp from rest. 2.5 seconds to get down the ramp from rest. Um, I'm going to say the end height is 10 centimeters. And I did ask you to estimate, I did mention to estimate how far it went from here, but I didn't write it down. Okay. Now I know where it ended up. It ended up about here. So let's just take that estimate. Okay, so what's the first thing you would be able to determine with that data? And different people might have different answers. Okay, so I got the answer, average velocity in the ramp. Well, that's really straightforward. I hope everybody calculated that. 90 centimeters over 2.5 seconds, 36 centimeters per second. Thought it took 2 seconds, you'd have 45 centimeters per second. If you thought it was 3 seconds, you'd have 30 centimeters per second. It's somewhere in that range. Okay. And 36 is probably pretty close to what you would have calculated. What I hope I see on your paper. I'm not going to grade these actually, but we're trying to prepare for lab and understand chapter 4. Okay. There we have average velocity in the ramp. So what would the next thing be? Somebody else answer. Okay, well, somebody said the acceleration. Well, that would be good, but we don't yet have enough information to find the acceleration unless you use something as a formula that you shouldn't be using as a formula without justification. Okay. You can draw a picture of velocity versus time. Velocity is 0 here, velocity is 36 centimeters per second. At the midpoint, so velocity up here. I would really like to see that picture, which takes you all of about 8 seconds to draw and label. If you're not thinking in terms of this, you have an 80% chance of making a serious mistake in calculating an acceleration when the velocity isn't 0. Okay. And of course, if the initial velocity isn't 0, you could draw a slightly different picture. V bar is still in the middle if the acceleration is uniform, and you can still figure out from the graph, similar triangles or whatever, just for common sense, what the final velocity would be, right? There are equations, there are formulas, and you should be able to use those too. But it's much easier and much more insightful to do it both ways. So I kind of recommend that you do that because this can be very quick. Okay, so I look at this, I quickly say, okay, average velocity, 36 centimeters per second, started at 0, final velocity, 72 centimeters per second. So the change in velocity from 0 to 72 centimeters per second, I divide that by the time interval, I get the acceleration, right? It's something you should see immediately. And you should also be able to put that into the formulas. But you don't need formulas. That's just straightforward reasoning about average rates of change. Average rate of change dictates every one of those steps, except the one where you use this graph to find out that that's double that. Okay, so anyhow, okay, so acceleration. It's pretty close to 29 centimeters per second squared. I'd even round it up to 30 because our estimates are so imprecise. We're not justified in making that distinction. But I think it's 28.8. But we'll just go with 29. We can deal with that number. Okay. So what was its average horizontal velocity while it was falling? Or if there's something else you want to determine, that's okay too. Okay, well, there was discussion, about what we want to determine. Okay, there are two things that we could determine at this point. It doesn't matter which. We could determine this, which I asked for, so that might not be a good, or that might be a good choice. Okay. Or we could figure out the time of fall. Okay. How long does it take to fall from here to here? Now, there's a complication with the time of fall. First, we're going to figure out the time of fall, just assuming that this angle is so small it doesn't make any difference. But that angle does make a difference because it gives this thing a little bit of downward velocity when it goes off the edge. If you assume that downward velocity is zero, which we will on our first calculation, you're going to be a little bit off. Not much, because that's not much of an angle, okay? But it's going to make a difference, probably in the thousandths of a second, okay? Maybe not even quite a thousandth of a second. We'll see, not even a millisecond. But it does make a difference in what you predict. Maybe not in what you would measure, but in what you predict. So we'll go with average horizontal while falling. Well, we had a little hesitation about this. Said, well, you use this and you use that and use the other thing. What's the average horizontal when falling? I'll say neglecting the cosine error, which is due to the angle. Noting horizontal velocity while falling is about 36 centimeters per second. Now, its horizontal velocity is actually 36 centimeters per second times the cosine of this very small angle. Well, cosine of a very small angle is very close to 1. So it doesn't really have an effect. But that's what I say by ignoring the cosine error. There is one, but it's probably not much over 1/1000th of the velocity, okay? Certainly nothing that's significant with the numbers that we've used. If you wanted to be very accurate, if it's a much steeper ramp, you'd have to take that into account. And you will, because that's coming up in lab, okay? Okay, so if we use this horizontal velocity, how are we going to get the time? Because that's what we want. Well, we got the average horizontal velocity. Okay, so what can you get from the average horizontal velocity? Well, I didn't list it, so you probably didn't address it. And I mentioned it just a little bit earlier. So, and I did mention it when I was putting this stuff down, but wouldn't necessarily expect you to have noticed it because you were copying stuff down. Okay, so I think I got it, 8 centimeters horizontal distance, right? If you have an 8 centimeter horizontal distance at 30 centimeters, 36 centimeters per second, well, it's 8 centimeters over 36 centimeters per second, which would be 2.25, it was 32. And 2, so it's about around 2/10 of a second, between 2/10, 25 and a quarter of a second. Okay, that makes sense? All I gotta do is divide 8 centimeters by 36 centimeters per second. And I'm gonna get 0.22 seconds. Got this lead, this distance, so I'm not gonna write down every detail of that. That's a kind of thing I would hope to be able to expect you to fill in yourself. We don't have to write out too much detail, but make a note of it if you're not sure. All right. So the other thing we can get, there's going to be an inconsistency. Because I don't think it takes 0.22 seconds to fall a tenth of a meter. Okay. Maybe around 0.15 or something like that, so it's not too far off. We can use this. It comes from these equations of motion with initial velocity 0, right? So that would be like the third equation. Gives you this, and I've seen people use this already. So that would be the square root of 2 times 10 centimeters over 980 centimeters per second squared. I chose to keep the delta S in centimeters because everything we're measuring here is in centimeters. And 9.8 meters is 980 centimeters. So 9.8 meters per second squared is that. And that's approximately then equal to the square root of 0.02, which is like 0.14. Okay. It's approximately 0.14 second. Now, I'd expect you to write out the details where you divide centimeters by centimeters per second squared, getting centimeters times second squared over centimeters, leaving you centimeters second squared in the square root, so you get seconds. I mean, you need to do that rather than just slapping seconds onto this thing without thinking about why. As I've said before, you've got to grab the wrong equation sometimes. And the units aren't going to work out, but if you think they work out, you're going to be stuck with maybe a critical error based on incomplete analysis and too much reliance on what you assume it to be rather than what it is. Physics will kick your butt every time if it gets a chance. And that's one of the ways. And of course, if you do have an error like that, you can think back to, well, why should it be this? Always be asking yourself, at least briefly, get in the habit of what's behind all this, what's going on. Okay? Not just how do I use these equations to get the right number. Okay? You don't have to spend a lot of time thinking that way. But spend 30 seconds thinking that way after you solve the problem. And if your brain wants to continue that thought for a minute or two, that won't hurt you either. It'll benefit you in the long run. Okay, so there we got t equals 14.14 seconds. There's an inconsistency. Is it a big inconsistency? Considering that we were estimating by I, okay? Would that inconsistency go away if it had been a 3-second time? Okay, so it had 30 centimeters per second. We'd have been a little closer. But there's the discrepancy. So you're going to measure things in lab. You're going to have inconsistencies. You're going to have to see where, well, if we do it this way, using this data, we find out that this thing that we measured ought to be 50% more than it really was. And if we use this thing that we measured, we find that this other stuff we measured is going to be that much different. And then you try to bring your inconsistencies together with your apparatus and your setup. Does that make sense? It's a big deal. Something I don't expect you to be an expert at right now. With my midterm, I expect to be pretty good at it. And I expect to be much better at it after lab than you are right now. Unless you're really good at it right now and don't have that far to go to be perfect. Okay, further you are from perfect, bigger the jump you can make. Okay. Well, that's just a little more about projectiles. Now, unfortunately, I haven't been able to look at the work you submitted because things have been pretty busy, and the test that I was designing took me like 6 times as long to design because I kept getting bugs in my program. That comes down to but I had to get the test ready. So I haven't had a chance to look closely or even look at some of the stuff you submitted since Monday. But I will for your assignment, your text assignment is about 10 more problems, maybe 11, but maybe even as many as 12, but no more than that. I counted them, then I decided, well, we need an extra 1 or 2. But I don't remember how the numbers ended up, but it's already posted. So I'll just put a date on it and then put the link to the video and maybe a few more comments, we'll see. But y'all been doing pretty well with the homework, so. Anybody run into anything they didn't understand on the homework? Anything you want me to clarify? So indicate and stop and you can tell me about it. We'll talk about it. Yeah. Now there's a question about range of a projectile. And somebody said they found an equation for the range, weren't sure how that worked in, and it's a good idea to ask about it. You're not sure what it means. First place, you don't need an equation for the range because you got everything you need if you know the equation of uniform accelerated motion. So you should ideally be able to derive the equation for range. But of course, doing a homework, 2 days after the first time we discuss it, you'll grab anything you can. Okay, I understand that. But make sure you process it. So I'm going to explain it here and see if that answers your question. There might be some esoteric thing about it. But I don't think there would be on the problems that I assigned, unless I made a mistake. Unless there's something in the problem that I didn't see. So it's just the horizontal velocity times the time of fall. Okay. The horizontal velocity, if you ignore the fact that this thing has a little bit of an angle, it's just whatever velocity it starts with. Okay. Now, in this case, we're going to assume it's a horizontal velocity. If it's not, then we got to find the velocity components. And I'll do that in another one. But I can do this one briefly just to clarify what the range is. So we'll just say, call the horizontal range delta x equals Vx delta t. Now the x velocity is always constant for a projectile unless we say otherwise. And we don't, to analyze a horizontal velocity where you've got air resistance, you need differential equations. Or otherwise you're just using a formula you can't understand. So we don't really do that. And I don't think the text does it. It's out of the scope of this course, though. So the only things in the scope of this course, as far as I'm concerned, is projectiles where the air resistance is negative. Even if it isn't negative. It says that I hit a golf ball at 110 miles an hour. That's slow. My swing used to be 110 miles an hour. Ball comes off at closer to 200. Okay. And some of the pros are getting up around 125. Big difference in energy. So if you say you hit a golf ball at 200 miles an hour, okay, and calculate how far it's going to go, ignoring air resistance, you're going to get a big overestimate because air resistance at 200 miles an hour is a big deal for a golf ball. But it takes advanced techniques to even begin to analyze that. And then if you take the effects of spin and everything, it gets totally bonkers. Okay? So we avoid bonkers with this assumption. We understand? Sir. Okay. So that ought to be, according to our estimates, I'll use approximately equal to 36 centimeters per second times 0.14 seconds. Okay. So 40 times 14 is 56, that'd be 5.6. It's a little, so I'm going to say it's about 5.4 centimeters. No, we'd have 36 and 144. It's like 5.04 if I multiply that out, I think. So I'm going to just get rid of all that. It's approximately 5 centimeters. I estimated 8 centimeters. Well, that was a very, I just kind of remembered where the ball landed, that I'd moved the ramp. So, that estimate was really suspect. but it wasn't that far off. You know, again, there's an inconsistency based on this time of fall, which is pretty interconvertible if that's 10 centimeters or anything close to it. It's I overestimated the horizontal distance. Okay, anyhow, that's the range. That make sense? Does that help a little bit? Now, was it a projectile that had some initial velocity other than horizontal? Don't say, because we got to just nod your head. So we'll do one of those. Say your initial velocity is 20 centimeters per second at 37 degrees. And for projectiles, that's by default measured with respect to the horizontal. But we would include that in our picture. So we would say that's a 37-degree angle there. It's a really bad looking arrow. That's a little better. Okay. So we have a picture, 20 meters per second at 37 degrees. You want to draw that picture. It takes just a few seconds to draw it, and then you have it to look at when you forget what the heck you're about, because you're sorting out something else. You can always go back to that picture and see where you started, and then you can add to your picture whatever is useful to add. Well, the thing that's useful to add is centimeters per second are written pretty badly there, because I'm spacing things well. Now, how do I get the X and the Y velocities? These basic right angle trig. The X velocity is going to be the length of this vector times the cosine of 30 degrees, 37 degrees, and the Y is going to be 20 centimeters per second times the sine of 37 degrees. Okay, so all right. I expect you to understand why. You've had trig. This is just right angle trig. You want to get used to that. Okay. You want to get used to what the cosine and the sine do. So review that if you need to. Go back to the definitions: opposite over hypotenuse and adjacent over hypotenuse. This is adjacent. There's the hypotenuse. So this over this is equal to the cosine of 37 degrees, which is 0.8. So this is cosine of 30 degrees times this times this. And this is so just as a reminder, but usually I'm not going to go to that much detail, but you should. It's a picture in your work, okay? The problem you're being assigned for Monday, problems it will do for today. It's too late to change your problems it will do for today if you've already sent them. But you want to write out the details that I'm skipping. Because I just want to take the time. I want to take the time to explain them either. I'll just say, there it is. Use trigonometry and verify. If you didn't already see that it was what it was, you probably did. Okay, so anyhow, So now we have X motion and Y motion. I would set it up like this. X acceleration equals 0. Y acceleration equals negative g. Then initial X velocity, 16 centimeters per second. Initial Y velocity, well, I wrote centimeters. And, I'm writing centimeters down here, so I was writing centimeters earlier. So let's get the C off of centimeters. All those meters. Okay. Then delta X equals what? Well, let's say this thing, standard problem, is falling a distance of 30 meters, which is further than you want to fall. Very high probability of dying, even if you hit water. So the projectile is going to go off this way. We're going to follow a parabolic arc, which can be modeled by a quadratic equation, a quadratic formula. Okay? You want to keep that in mind. Your delta X is going to be what? It's going to be negative 30 meters. By saying that the acceleration it's about the 40th dumb thing I've done. Delta Y, it's negative 30 meters. Delta X is your range. And that's what we're trying to find. So what's the range? Well, we've only got two quantities for the X motion. We don't have time, we don't have the final velocity, and we don't have the displacement. All we've got is the initial velocity and the acceleration. What can we do with the Y? Oh, we got three things there. We have the displacement, we have the initial velocity, we have the acceleration. Okay. We know if we have three of these, we can use the equations of motion and find a fourth. If that fourth happens to be the time, we can put it over here. Time is going to be the same for the X motion as for the Y motion. And there's the key to solving most projectile problems. They share the time. Okay. So anyhow, I'm not going to do it interest of time because there's another topic we need to talk about. All for delta T, and then use delta T here. So delta X equals V bar delta T, Vx bar. Noting AX equals 0. So that Vx bar equals the initial X velocity. If the velocity isn't changing, then that is the average velocity. You only have one velocity. That's it. Most projectile problems. You might have different information for the Y. It might ask, okay, it's going to hit a wall that's 40 meters high. And this far away. that gives you information you can put into this scheme. But in any case, for the problems I gave you, for the most part, you're going to have three quantities on one side or three quantities on the other. And it's usually going to be three quantities over here. You just have to identify them and solve for delta T. And over here then becomes pretty easy. It's not always the case, but start out with that model and then think about why it's so, and think about what's changed and what you might do. The hard problem is one that we're going to talk about in lab. If the angle of this thing is significant, and all we know is the range, how do we find the velocity when it came off? We know the angle and we know the range, but that gives us a theta on this side and a theta on this side. It's the same theta. But that's what we have in common, and it gets a little more complicated, a little harder to understand. I had a hard time understanding when I saw it. My algebra and trig were great, but it still got messy and confusing. Okay, took me a little while. Okay. Does that help a little bit? The situation. If you want, after it's got time, you can show me the equation. But basically, the horizontal range then would be calculated with a formula where you use V naught y equals V naught sine theta, V naught x equals V naught cosine theta, and do it with symbols. And if you just do everything I'm talking about here with symbols, you get a formula that you don't need and shouldn't use in lieu of the basic principles. Okay. But of course, you just gotta, we'll go ahead and use it. But then come back and say, why did I have to use that formula? What could I have known? And think about it. Okay. There's a really good problem in the university physics text. And I had a student some years ago, a bright student, but compared to his brother, he was a complete zero intelligence, because his brother is the third most brilliant student I've ever taught. The most brilliant had an IQ just short of 200. This guy was probably a 160 or so, which is Einstein level, without necessarily creativity. The guy I'm talking about, brother, thought he had a proof of the four-color theorem. Have you heard of the four-color theorem? Very famous problem that was unsolved until sometime 30 or 40 years ago. When I started here, it was unsolved. Okay. Just, can you always color the map of a bunch of regions with only four colors so that no two colors are touching? No colors touching itself, sorry. Okay. And this guy kept coming back to me, he was still in high school, with proofs that I had to puzzle over because he wasn't expressing them very well. Okay. He wasn't really saying what he thought he was saying. He was saying something that he intuited that I couldn't figure out. So I had to keep pressing him until he put it into real terms. And then I boiled it down to, okay, here's a step. I don't know if that step is valid or not, neither do you at this point, but that's where I focus. Well, he went on to UVA and immediately started pestering one of the professors there. He said, okay, I'll look at it one time. So put it in form, give it one look. Took one look. He said, we're going to have to go to the library where they have a compendium of false proofs, famous false proofs of this thing people believed for a long time. And his was one of them. He was 17 years old at the time. Okay. Now, why did I mention this? His brother could still be an A student in this course, but, not within a 10-mile football throw of his brother. And I'm not either. Okay, his brother's really, really something. Had one of my favorite problems was assigned out of the book that I've always used, that I no longer use because you have to buy it. And it was in something in electromagnetism and cosmology. And it took some real reasoning, but people sometimes got it. Well, he went out and found a formula for it and solved it with a formula. I said, that's not a solution. You didn't solve it. Okay. And I had to, he was the kind of guy you had to take a little bit of a stern approach with, because he's a little unfocused in some ways. And he's fine with it, So he didn't do that anymore. I mean, I didn't. He was doing it as a distance student, so I just put a somewhat critical note in there. You can't do that. That's not a solution. That's not based on what you're learning in this course. That's based on something that somebody at a higher level derived and put on the internet, and you have no idea where it came from. So kind of take a lesson on that. Try not to be in that position with formulas that aren't really basic. Try to identify what's basic. You won't always be able to, and sometimes you're going to have to use a formula. Formulas are what you use when you get to the end of what you know. And then you hope you got the right one. And engineers do it all the time, but not in their physics classes, if they can help it. Okay. So, yeah, this guy thought he was using good initiative to go out there and find a formula to solve. And I did say, yeah, that's not bad initiative, but I don't accept it. Okay, well, oh Lord, I haven't left myself much time. I shouldn't have digressed that much, but anyhow, here we go. A couple of other topics. One of them is centripetal acceleration. Now, you've read, if you've been reading, or you should have been told that by the time you were 12 years old, about, an object is in motion. It's going to stay in motion in the same direction with the same speed unless some force acts on it. So no net force, no acceleration is basically what that's saying. So are these magnets? Let's just assume I've got a motor and this thing's moving at a constant speed. So we're not going to worry about the fact that it is speeding up or slowing down a little bit with an acceleration you've calculated already. Okay, angular acceleration. But let's just say, pretend it's constant. Okay, how do I know that this magnet right here is accelerating? Angular acceleration, the angular velocity is constant. The speed of that thing is constant. What's its acceleration? Why does it have an acceleration? Well, it's not moving in a straight line at constant speed, right? Let's give it constant speed, but it's not moving in a straight line. So the essence of this argument that you want to focus on when you read about it is you have problems. What are you to know it? This thing's moving on a circle. Here it's got a velocity in this direction. Here it's got a velocity in this direction. Is this vector the same as this vector? Why? Because this vector starts here and this vector starts here? No, because the angles of the vectors are different. Their magnitudes are the same. They have the same length. So I can draw these vectors with the same initial point. No, I can just move these vectors together down here. the change in velocity is this vector minus this vector. Now, if you know how to add vectors and so forth, you can do that, okay? Like you reverse V1, okay? Then you add them head to tail and you get this vector. And you should be able to do that. Go back and look at how to add vectors graphically. It's in the first chapter, I think. Okay. This chapter goes pretty deep into vectors, into dot product, even cross product. You need to have everything up through dot product for this course. Told you that a couple of weeks ago. So if you haven't done it, try to find a time to do it so that you understand the vectors here. Okay, well, if there's a difference in the velocities, then there's an acceleration. That's your delta V. So your average acceleration is delta V over delta T. The change here divided by the time it takes to go from here to here. This leads to the fact this acceleration, among other things, if you make this instantaneous, these vectors are almost parallel, just a little tiny difference. Of course, there's a little tiny time that you divide by, and taking the limit, you get something that's very close to what you get here. But that angle, these vectors have the same magnitude, so that angle here is the same as this angle here. If this angle approaches 0, then these angles approach 90 degrees. That makes sense? So the acceleration is centripetal, 90 degrees to the velocities right toward the center because of the geometry of a circle. The velocity is tangent. A tangent line is perpendicular to a radial line. That's basic circle. Again, if you don't know that, you really want to understand why this is true, and you really should understand the proof, because proof is really just about high school level. Okay? Just about. It's at the level of a non-calculus physics class. That's centripetal acceleration, and that's something you're going to need. Because now, if that thing is moving at 1 radian per second at 30 centimeters, then it's moving at 30 centimeters per second, right? Whether you understand that or not, you can put the distance from the center and the angular velocity together and figure out how fast it's moving. That's your V. 30 centimeters per second squared, you get 900 centimeters per second squared. Divide that by 30 centimeters. Okay. You get, well, it was 900 centimeters squared per second squared. Divide that by 30 centimeters, and you get 30 centimeters per second squared, or 0.3 meters per second squared. And that's relevant to whether an object resting on the end will stay on the end. Is it needs too much centripetal acceleration, friction's not sufficient to keep pulling it in. It just accelerates off. Okay, well. So you have to do some reading on some of it. And some of the problems might be, I'll look at them again, make sure they're all fair problems to ask you to do for Monday. And if not, I'll maybe take a little time on Friday and fill some of the details in. But the big one you need is centripetal acceleration is V squared over R. Read about it. Not that hard to understand. Once you understand it.